All right, let's talk about something that's literally all around us, but completely invisible. It's the unsung hero that makes your phone calls, your Wi-Fi, your radio, pretty much everything possible. We're talking about modulation.
To get our heads around this, let's start with a really simple question. A little thought experiment. Imagine you need to get a note written on a piece of paper to a friend who's, say, 50 feet away. How do you do it? I mean, if you just crumple it up and threw it, what's going to happen?
Yeah, it just kind of flutters and falls to the ground, right? It goes nowhere. That piece of paper, just like the sound of your voice or a stream of data, is what engineers call a baseband signal. Basically, it's the original message, raw and unboosted. It has all the information, but it's just too weak and low frequency to travel any real distance on its own. So, how do you solve the paper problem? Well, here's the thing. You don't change the paper. You give it a ride. And this is the genius trick behind all wireless communication.
Think about it. You wrap that note around a stone, right? The stone is heavy, it's strong, and you can totally throw it 50 feet, no problem. This is exactly what modulation is. We take our weak message signal, the paper, and we wrap it around a strong, high-frequency carrier signal, the stone. The message gets to hitch a ride, and on the other end, your friend just unwraps the paper to get the message. Simple as that.
And this really breaks down the two key players in this whole operation. You've got the message signal, your voice, your data. It's low frequency, it's weak, it can't go far. And then you have the carrier signal. That's the ride. It's a powerful, high-frequency wave that's awesome at traveling long distances. But here's the catch. It carries no information by itself. It's an empty vehicle. Modulation is just the magic act of combining.
So we get what modulation is, but why is it such a massive deal? Why is it a total game changer? Well, it turns out this one simple idea delivers three enormous engineering wins that literally make our modern world possible.
First, it shrinks antennas from some impossibly huge size down to something that can actually fit in your pocket. Second, it's what allows thousands of different signals to fly through the air at the same time without turning into one big chaotic mess. And third, well, it's the whole reason we can even have efficient long-distance wireless transmission in the first place.
Let's really dig into that first win, because it is truly mind-boggling. You see, the size of an antenna is directly related to the wavelength of the signal it's trying to send, and low-frequency signals, like the sound of a human voice, have these enormous wavelengths. For an antenna, that creates a physical problem that's almost unbelievable.
How big are we talking? To transmit a simple 10 kilohertz audio signal without modulation, you would need an antenna roughly 7.5 kilometers tall. No, seriously, that's almost the height of Mount Everest. It's completely absurd. But by modulating that signal, by giving it a ride on a high-frequency carrier, say at 10 megahertz, the required antenna size shrinks down to just 7.5 meters. That's the power we're talking about.
Now, that second win is just as crucial. Imagine if everyone's cell phone calls, all the radio stations, all the Wi-Fi signals were broadcast at the same low frequency. It would just be a wall of noise, total chaos. Modulation allows us to assign each signal its own unique high-frequency carrier. This is called frequency division multiplexing, and it's the reason you can tune your car radio to 97.1 FM without hearing the station at 102.5 FM bleeding through.
So we've covered the why. Now let's get into the how. How do you actually imprint a message onto one of these carrier waves? Well, for analog signals, it's all about changing the wave's fundamental properties.
The first method is amplitude modulation, or as we all know it, AM. This is the simplest way to do it. Imagine the carrier wave is just a steady, constant tone. In AM, you make that tone louder and quieter, exactly matching your message signal. The height, or the amplitude of the wave, changes. It gets taller and shorter, but its speed stays the same. The second way is frequency modulation, or FM. Now here, the height of the wave stays totally constant. Instead, we change its speed, or its frequency. So when the message signal is high, the carrier wave oscillates faster, it bunches up. And when the message signal is low, it slows down and stretches out.
So why have both? It all comes down to a classic engineering trade-off. AM is very simple and cheap to build, but because its information is stored in the wave's height, any random noise, like static from a lightning storm, can easily corrupt it. FM, on the other hand, is more complex, but since its information is in the timing of the waves, not their height, it's incredibly resistant to that kind of noise. And that's exactly why FM radio sounds so much clearer than AM radio. But, that's the analog world. Today, most of our information isn't a smooth wave. It's digital. It's a stream of ones and zeros. So how on earth do we modulate that?
Well, the thinking has to shift completely. Instead of just mapping an analog wave directly onto the carrier, we first have to convert that analog information, like the sound of your voice, into a digital code.
And the most common way to do this is with something called pulse code modulation, or PCM. It's a three-step process. First, we sample the original analog wave, taking thousands of little snapshots every second. Second, we quantize each of those snapshots, which just means we assign it a numerical value. And finally, we encode that number into binary. That resulting stream of ones and zeros is what gets modulated onto the carrier wave.
Okay, let's bring this all together and see how these different methods are powering the technology you use every single day. Because once you know what to look for, you realize modulation is absolutely everywhere.
This chart lays it all out beautifully. You can see how that simple AM method is still powering things like AM radio and is used in aviation. FM gives us that clear radio sound, but the real powerhouse of the modern era is QAM. It's this hybrid technique that changes both the wave's height, its amplitude, and its timing, its phase, at the same time. This clever combination lets us pack an incredible amount of digital data into a single signal. It's the engine behind your Wi-Fi, your 5G connection, and high-definition TV.
So, the next time you send a text or stream a video, just remember the invisible ride making it all happen. Every bit of data is like that piece of paper, hitching a ride on a carrier wave, all thanks to the genius of modulation. And it really makes you wonder, as we demand fast